Man, does this reaction look complicated, which is why it's a great idea to start any balancing problem with a quick atom count, or a less quick atom count if you happen not to be great at it yet, but that's okay. Here is that atom count. Reorganizing shows that there are really only 4 things to worry about, that 2 of those 4 things already appear balanced, and that the other 2 things are really not very far away from being balanced. As a note, I divided up the oxygen count this way in case it is difficult for someone to move from the equation straight to the total. There are 2 oxygen atoms from the magnesium 4 oxide and another 4 in the oxalic acid. That gives us a total of 6 on the reactant side. Similar story for the counts on the product side. Of the things that aren't balanced, carbon is the easier to deal with as oxygen is found in all 3 compounds on the product side. So I'll begin by doubling the number of carbon dioxide molecules present on the product side. This changes the carbon count to 2 and also gives me the 2 missing oxygen atoms. So we are all done with this one. This has a couple of polyatomic ions, so I need to remember to balance the ammonium and nitrate ions as groups and not as individual atoms, giving me a table that looks like this. My table implies that my iodides might be a good place to start. I need twice as many as I currently have on the reactant side to get it to match the product side. So I will double the number of ammonium iodides by adding a coefficient of 2, and then I will update my table. Adding that coefficient squared away the iodides but unbalanced the ammonium cations, so I'm going to follow that rabbit hole now and add a coefficient of 2 in front of the ammonium nitrate that's found on the product side. That finishes this off. Start by counting things. There's 5 different types of atoms. Don't panic, it's the same thing, only different. Just pick something to start with. I would probably start with the oxygen here because it sticks out to me as having the largest difference. And it's only found in one spot on each side of the reaction arrow, so there's only one place on either side that I could go to make these equal. Since I need to end up with 3 oxygens on the product side, I'm going to add a coefficient of 3 in front of the water and then update my chart. I might as well work on the hydrogen next, since that 6 seems silly all by its onesie. A 6 in front of the HCl will balance the oxygen atoms, but throw the chlorine out of whack, which leads me on to chlorine. I need more on the product side, so I'll have to increase the number of KCl formula units in order to balance that chlorine. The last coefficient threw potassium out of whack, so here I have 2 options, but really only one good one. If I mess with the KiO3, then I also mess with the oxygen atoms that I balanced first, which would in turn mess with everything that I've balanced since. Well, there will be times that you actually do have to do this. You want to avoid it if at all possible. So I'll add a coefficient to the Ki instead. I need a total of 6 potassium on this side of the equation, but I have 1 already with the KiO3. That means I'll have to add a coefficient of 5 in front of the Ki. That 5 gives me a total of 6 potassium atoms on the reactant side and a total of 6 iodine on the reactant side, which makes my final step adding a coefficient of 3 to the iodine on the product side. This gives me 6 iodine atoms and balances the entire equation. Here you'll need to move from the words to an unbalanced equation before you can actually balance an equation. These are a great way to practice your nomenclature and keep fresh with it. Here's your unbalanced equation. In this form, it's a lot more clear that this is a combustion reaction, and we know that if we balance our atoms in a certain order for a combustion reaction, our lives are much easier. It means we will start with carbon. To balance it, we'll add a coefficient of 5 in front of our CO2. Hydrogen is second on our balancing list. Again, a coefficient of 5 is in order. However, this gives me an odd number of oxygen atoms. So at this point, I'm just going to double the coefficients that I already have and then count my oxygen atoms. There are going to be 20 associated with the CO2 now, and another 10 that are associated with water. This gives me a total of 30 and means that I'll need 15 oxygen molecules in order to balance my equation. You should aim to include the states of matter on this one, but if you didn't know the sodium hydroxide, don't fret. That's actually covered in the next section. The rest are more reasonable, as sodium is on the metal side of the periodic table, water is the common name for the liquid form of H2O, and you're told hydrogen is a gas. More importantly for now, make sure that you work to remember that hydrogen gas is a diatomic element and will appear in equations as H2 and not H. And lastly, it might help to think of the water as HOH to more easily deal with those hydroxide ions. In the interest of nudging you towards working through these quickly prior to your quizzes and exams, I'll walk through this one without a table. Your goal prior to the quiz is to get to the point where you can work through these in your head in a similar manner to what I'm going to do here. Being able to do this for even the simplest ones will save you some time and let you put that time towards other questions come quiz day. Review the entire equation and you'll see that we have to balance sodium, hydrogen, and hydroxides. Working from left to right, it looks like the sodium is okay, so I'm skipping it for now. Moving on to hydrogen, we have a single hydrogen on the reactant side and 2 hydrogen atoms on the product side. If I have 2 waters instead of just 1, the hydrogen atoms will balance. This now gives me 2 hydroxide groups as well, where there's only 1 hydroxide group on the product side. Doubling the number of sodium hydroxides will balance those. Lastly, that action threw the sodiums out of balance, so we have to go back to our left and add a coefficient of 2 in front of the sodium metal. Transfer the names to chemical formulas. Keep an eye on your transition metal complexes. They include 2 different oxidation states. Also, don't let the iodine get you. It's diatomic. If you didn't include it as a diatomic molecule, you won't be able to balance the equation correctly. You should include states of matter for everything because they are all given in the problem. However, in the interest of being able to actually read the equation from this video, I've dropped them out of what I will actually balance. I'll start where many of you probably will, which is moving past the copper, which appears to be balanced, and on to the nitrate. Adding a 2 to the sodium nitrate takes care of those nitrate anions. Then you can add a coefficient of 2 to the sodium iodide to balance the sodiums. At this point, you may have noticed that doing so gives you an even number of iodides on the reactant side and an odd number on the product side. There's not a terribly obvious way to balance these iodines without messing with the sodiums, and then the nitrates, and then the coppers. If you get into a situation like this, I strongly suggest doubling what you have come up with before you carry on. If you do so and you get to the end and everything can be halved, that's great. Do it at that time. Doubling balances the sodium, but we need to revisit the first copper compound to balance the nitrate, which lastly means that we need to balance the copper atoms on the product side. This last coefficient also balances iodine.